You can mute yourself. When you say something, we will have a feedback. I should be able to.
Yeah, mute me.
I can remove you. How about that?
Why am I not seeing this? So I'm still not muted. I don't know why I'm not seeing it.
Oh, you're not connected to audio. That's even better.
Okay.
So you can share the screen and then I'll answer you and then you'll know.
Should I share my screen right now?
You're sharing your screen.
Right now?
No, in your presentation.
Yeah.
And then you'll go through the Zoom to this computer.
Oh, how'd you do that? Wow, that's neat.
It's ready.
Good job.
Okay, everybody. It's yeah. So we had the announcement, as you probably seen, the medals for 2022 was announced. So you see the number. The people actually received it. There was some suggestion to make a separated session about it, and we're happy to do so if you're interested. But before that happens, we have Nick Scoville, who will want to speak about some recent results of the homotopic type of the Morse complexes or complex. Just one, so just complex.
Thank you very much for the introduction. Thanks everyone for being here, and thank you not only to Pavel, but all the organizers for organizing this conference. I'm very happy to be here. I was at this first Applied Topology conference in Będlewo back in 2013, and it very quickly became my favorite conference. I was here back in 2017, so I'm very excited to be here. So today I want to tell you about some recent results on the homotopic type of Morse complex. This is the culmination of several papers with several co-authors, including my current student, Connor Donovan at Ursinus College, Max Lin from the University of California, Berkeley, as well as Matt Zaremski from the University of Albany. And I suppose I need to kind of apologize up front. This is a talk on discrete Morse theory, which it has a lot of nice applications to applied topology. You can use it to simplify your space. You can use it to estimate Betty numbers, compute homology. There's a lot of really good things you can use discrete Morse theory for in applied topology. Unfortunately, I won't be talking about any of that. This is a very much a pure mathematics kind of talk. So I appreciate you bearing with me, and hopefully you'll at least see some pretty pictures. And if people can think of some ways in which you can use these ideas to model some real world applications, I would love to hear about it. I'd love to know. So that being said, let me tell you about some of these recent results. So I first want to introduce my main object of study. I'm going to work with a simplicial complex, abstract simplicial complex. I'm not going to go into the geometric simplicial complex. This is going to be nice and simple. So there is the 2 simplex up there. And what I'm going to be interested in doing is putting certain collections of arrows on these simplicial complexes. There you can see 4 different examples of the kinds of collections of arrows that I want to put on them. Let's see exactly what I mean by these collections of arrows. So actually, I'm going to be putting 2 different kinds of collections of arrows. One of them I'm going to be a little bit more interested in, and hopefully we'll make sense of this. So I want to define something on a simplicial complex called a gradient vector field. And this is going to be a pairing, a matching of the simplices of my simplicial complex. They have to differ in 1 dimension, and sigma has to be a subset of tau. And it has to be a matching in the sense that every simplex is paired with at most 1 other simplex. Each simplex has 1 partner at most. So you can't have 2 partners. And so this is a matching in kind of the classical graph theory sense. Okay, So that's going to be a discrete vector field. And you can see how I kind of have those modeled here with the arrows. If I have a p-1 simplex, maybe that's starting at the arrow starting at a tail, and it's moving into the p simplex at the head of the arrow. And so you can kind of follow these arrows along. They are kind of mimicking what this matching is doing. I'm going to be a little bit more interested in gradient vector fields, though. These are discrete vector fields. They are matchings on my simplicial complex, satisfying these properties. But what I want to exclude in a gradient vector field is a closed loop. So I talked about this idea where you can kind of think of these arrows as giving me a direction. I start at the tail of an arrow and I follow it to the tip, and I see if there's another tail and I begin to follow that. And if I eventually end up where I started, I'm going to call that a closed loop. And I want to exclude those for a gradient vector field. And you can see an example here of a closed loop on the second one there on the left. Okay, for the most part, I'm going to be interested in these gradient vector fields, but we will do some stuff with discrete vector fields. Okay, so I've got simplicial complexes. I'm putting these gradient and discrete vector fields on my simplicial complexes. What do I want to do with them? Well, this Morse complex, this main object of study that I want to think about, I'm going to illustrate with the following example. So here is the boundary of the two simplex. I'm going to label the vertices A, B, and C, and I'm going to put a gradient vector field, or really a discrete vector field, on here consisting of a single arrow. Okay, nothing too exciting, and I want to give that a name. So if I have a gradient vector field with a single arrow, I'm going to call this primitive, or just simply an arrow. And the idea that I'm going to put forward, the thing that I'm going to be doing, is I want to think about taking these arrows, these gradient vector fields, and seeing if I can overlay gradient vector fields on top of existing gradient vector fields, and if they're compatible or not. If I put some down together and I get, multiple matchings, that's no good, or closed loops. These are the things that I want to think about. So I'm going to call this a primitive gradient vector field. And what I want to do is on the right, I want to have a vertex to represent that gradient vector field. It's the matching vertex C with the edge CB. So I will represent that there on the right with a vertex. Well, I can do that for any one of these primitive gradient vector fields. Here I have the primitive gradient vector field B, BA. I'll represent that with a vertex. And I'll represent this other primitive gradient vector field here with a vertex. Of course, there's nothing special about arrows going, I guess, what is this? Counterclockwise. I could also have my arrows go clockwise as well. And so there's 3 arrows going that way. And again, for each primitive gradient vector field, I'm going to associate a vertex to it. Okay, so far so good. Well, now the question becomes about whether or not I can overlay arrows on top of one another. Are there compatible primitive gradient vector fields? So for example, I will take the gradient vector field CCA, and I will try to overlay AAB. Sure enough, this is a legitimate gradient vector field, and so I'm going to draw an edge between those 2 corresponding vertices there on the right. And so you can kind of see the name of the game that I'm doing here is I'm looking for all possible compatible gradient vector fields, and I'm beginning to build a simplicial complex there on the right, associating a complex to all these gradient vector fields. And so I'll just go through and keep finding all possible pairs of gradient vector fields. As I'm doing this, I'm drawing the edges between the corresponding vertices, and I'm beginning to build some sort of object. Okay, so these are all the pairs of gradient vector fields. Let's look at triples now. Well, I didn't point it out earlier, but there is a nice kind of geometric representation of when you don't have a matching, namely something like this. Here there's 3 arrows on there, but of course this is illegal. This is saying that A is matched with both AC as well as AB, and that's something that I said I'm not going to allow. Everybody is in at most 1 pair. Okay, are there any other ways to have a triple of vectors? Well, I could do this, and I could have a closed loop. Yeah, Pablo.
Can I prescribe some services critical? I want A to be critical.
It depends what you mean by critical. Right now, I'm just associating one simplicial complex to another. And so it might depend what you have in mind by critical.
Science question about functions.
Yeah, I might have missed it.
I think you're doing
Okay, yeah, possibly. Yeah, maybe we can talk more about that. But I mean, so there is, of course, a notion of criticality in discrete Morse theory, but right now it's just, oh, I've got these things, and we'll see some critical things coming up eventually. So the idea here, though, is that I've got this closed loop of vectors, and now it depends, do I want to be considering the gradient vector field where I'm not allowing that, or the discrete vector field? And as I said, for the most part, I'm going to be interested in the gradient vector field. So I'm going to exclude this for now, and I want to give this object that I've just constructed a name. So I'm going to define the Morse complex of a simplicial complex to be the simplicial complex of all gradient vector fields on K. In the literature, this is also called the complex of discrete Morse functions. And so I'm interested in studying this object and figuring out some properties of it. If we do pass to the collection of all discrete vector fields, if we do allow closed loops, you can see this is what we would get. I'm going to call this the generalized Morse complex. And this is actually, if you think about it, the flag complex of the Morse complex. And we'll use that fact a little bit later on, realizing that this is in fact a flag complex. Okay, so I've got the Morse complex, I've got the generalized Morse complex. At this point, I want to point something out just in passing, because we'll use this a little bit later, but this makes a nice tie-in. I neglected to mention that this construction that we're doing, it's along the lines of things that people in combinatorics have been doing for quite a while with graphs. The matching complex, the independence complex, the neighborhood complex, things like this. And there's this pretty simple relationship between the generalized Morse complex, or all discrete vector fields on a fixed simplicial complex, and matchings on the barycentric subdivision of a graph. So I guess I have to have a graph here on the right. And so I can associate in the following way to any discrete vector field a matching on the barycentric subdivision and vice versa. So this is kind of a nice little relationship between the two. And I just, again, want to mention in passing the fact that if I'm looking at a tree, well, the Morse complex of a tree, there are no closed loops. So it is a flag complex, and it is the generalized Morse complex. And so it's the same as the matching complex of the barycentric subdivision. So any result that I have about the homotopy type of the Morse complex of a tree, this will also apply to the matching complex of the barycentric subdivision of that same tree. So there's some interesting connections here. I'm not going to go too deep into them because I don't know too many of them, but this is something to kind of keep in mind. Okay, so when it comes to why am I interested in this Morse complex, this complex of discrete Morse functions? Well, there was this result back in 2017 due to Gabriel Ninian and his PhD student Nicholas Capitelli, where they show the following. They say, if you hand me two Morse complexes and I look at the isomorphism types, they have the same isomorphism types, then they actually must be coming from isomorphic simplicial complexes. And so in some sense, these gradient vector fields, these collections of all gradient vector fields, they are completely encoding the precise simplicial structure of my object. So I thought that was a little bit surprising that this gives me a complete description up to isomorphism of these simplicial complexes. So I found that to be pretty interesting because, okay, we're not so much interested in the exact isomorphism type. We tend to be more interested in topology or homotopy type. And so what happens if you descend to the level of homotopy? Make something a bit weaker, but what happens when you do that? Well, as we'll see in a little bit, this question, it doesn't work, this idea doesn't work at all in the Morse complex setting. So I can hand you two Morse complexes that are both contractible, and they could be coming from any homotopy type you want at all. So you try and ask the same question on the level of homotopy type, and it's all fair game now. So I thought this is a very interesting kind of thing. There's a lot to be done with the homotopy type, and so this is one of my kind of motivating theorems that I was looking at to say, okay, this seems like an interesting thing that's worth studying. So what is known about the homotopic type of the Morse complex? Well, not too much. The results that we have so far are given by our own Dmitry Kozlov, where in a little bit of a different context, he was able to compute the homotopic type of the Morse complex for a path, as well as a cycle on a graph. And so what homotopy type you get, this is going to depend on the number of vertices you have mod 3. So this is an interesting result. I get some spheres, I get something that's contractible, wedges of spheres, things like this. But for the most part, when it comes to homotopy types of classes of simplicial complexes, this is about all that we know. There's a few random particular examples that we can compute the homotopy type for, but this is about, as far as I know, all that is really known. Okay, so with that, let me share with you some of the results that my collaborators and I have come up with. And I'll show you a few different techniques, different tools that we've used in order to compute this homotopy type. And hopefully you'll see we're not doing anything too crazy, not too bad. It's nice and combinatorial and such. So I'm going to begin by making the following definition. I will define an arrow, primitive gradient vector field. I will say this dominates another arrow if every gradient vector field containing the alleged arrow that's dominated is compatible with V. Now there's a little bit more, this is a kind of specific example of this definition. This definition is a little bit more general. You can apply it to simplicial complexes, but for our purposes, I'm going to define it in terms of arrows. Let me give you an example of how this works. So here's a simplicial complex. There are a couple of arrows, and I claim that the blue arrow V dominates this red arrow V prime. So let's see, what do I need to check in order to see if this is the case? Well, I need to check that anytime you have a gradient vector field that contains V in it, V prime in it, I can overlay V on top of it, and it will still be a bona fide gradient vector field. So let's at least illustrate that with one example. So here is a perfectly valid gradient vector field that contains V prime, and I want to ask, can I kind of overlay V on it and have it still be a gradient vector field? And let's see, sure enough, this gives me a nice gradient vector field. And you can check for all possible gradient vector fields that contain V prime, V can be overlaid on top of it and you still get something. So V dominates V prime. Well, as I like to say to my students, whenever you are trying to understand a definition, it's helpful to see examples of the definition as well as non-examples of the definition. So let's, in order to make sure we understand this, see something that doesn't work. I claim that W does not dominate V prime. Why is that? Well, I'm going to take some gradient vector field that contains V prime. In fact, the very same gradient vector field that contains V prime, I'm going to try and overlay W on top of it, and oh, this doesn't work. I've matched this edge twice. Yeah?
Should V and V prime be lower adjacent or upper adjacent? Is it necessary? Because
So I'm not sure what you mean by lower and upper adjacent.
V and V prime are in the edge, which share one vertex.
Oh, in order for this to be the case?
Yeah, I mean, because I guess that could be related to this compatibility.
Yeah, so I think if I'm understanding, at least maybe part of what you're getting at is I have a good chance, in general, the answer is no, because I can begin to remove other arrows. So it's going to kind of depend. Right now, we're starting with in general, the answer is kind of no, and I can explain why a little bit later, but maybe what you're getting at is the idea that if I have an arrow on a leaf, this is going to be compatible with most things. And I think part of the idea is that the only thing that an arrow pointing downward on a leaf is not compatible with is the other arrow going up into it. And this red arrow is blocking the existence of that arrow. That might be what you're getting at, yeah. Yeah, so that's a good observation. In general, though, we'll be pulling arrows off, and then that might not necessarily be the case. But at first glance, yes, that's right. And we'll give a theorem about that in a minute. So far so good. Anything else? All right. So that's my idea of dominate. Oh yes, and so that's illegal. As we mentioned before, it's very illegal to do something like that. Okay, so how can I use this? Well, there's a nice little result, not too bad, due to Barmach and Minion. again, in a more general context of simplicial complexes, not in the language of arrows and Morse complexes, but which says the following, that if you have a simplicial complex and you look at the Morse complex, and if you have an arrow that dominates another one, then there is this simplicial map from the Morse complex to the Morse complex with that arrow removed. Okay, fine. We're going to call this a strong collapse. And if you've seen collapses before in the context of discrete Morse theory and such, this is generalizing that idea. The upshot of all of this is the following, that this Morse complex, when I remove the vertex that's dominated, it has the same homotopy type, in fact, what's called strong homotopy type, as the Morse complex. So what this does for us is this allows us to say, okay, if I'm interested in the homotopy type of the Morse complex, I can find these dominating arrows, hopefully, and I can begin to remove arrows that are dominated to do a little bit of pre-processing, kind of wilt this down and see if I can get to something a little bit more manageable. So this is a nice way to, if you've got them, begin to compute homotopy type. So how will we use this? Well, we can use this to prove the following. So we can show that if you have a simplicial complex with two leaves coming out of it sharing a single vertex, then the Morse complex is actually strongly collapsible. In particular, it's contractible or collapsible, however you want it, but it's also strongly collapsible. And this is actually pretty easy to see. So here are my two leaves coming out of a single vertex. Inside this dotted area, I can have all kinds of crazy stuff going on, who knows? But I want to argue that I can essentially collapse this entire Morse complex down to a single point. And the way I'll do that is by finding a couple of dominating arrows. So first, I claim that this red arrow is dominated by this blue arrow. So again, think about the name of the game is that every time I have a gradient vector field containing the red arrow, I can overlay the blue on top of it. The only thing that might stop that is if I had an arrow coming out this way. Well, of course, that's illegal. I can't do that. The fact that I have the red arrow coming out of A means I can't have something else coming out of A. So I've got this blue arrow here dominating the red arrow, and now I can pull this red arrow off. It's no longer a player. It's no longer an option for building a gradient vector field, and that's going to be important. And that might address a little bit the question we heard earlier, because now I claim that this CCA, this arrow, dominates the entire simplicial complex. And so that I actually have now what's left a cone with apex CCA. So think of any gradient vector field you could possibly put on there. The one that might be compatible has already been pulled off. We pulled the one arrow off that could possibly stop this from being compatible. Therefore, this vertex dominates the entire graph. So the entire thing is collapsible. And in fact, strongly collapsible. It's a cone at this point. So just to tie this into something I said earlier, an immediate corollary then is that if you have any graph, and I guess you can prove it in a similar way, if you have any graph with two leaves sharing a common vertex, then the matching complex of the barycentric subdivision of that will also be strongly collapsible. It'll have that homotopy type as well. You essentially get that for free. Okay, so this is a pretty general result, and it shows that there's some, you can have a very complicated object and maybe get a crazy Morse complex, but then you add these two little leaves on a vertex and it just becomes contractible. So this is almost like a coning operation. It's very sensitive to these kinds of things. Okay, so what this does in particular for us is compute the homotopy type of the Morse complex on all trees, for example. So this will allow us to, it's okay. This will allow us to say that, well, if I have any tree with two leaves coming out of a single vertex, its Morse complex is contractible. Okay, let me look at a couple of other examples. If I'm looking at maybe the Morse complex of a cycle wedged or joined with a single leaf, we saw that Dimitri was able to compute the homotopy type of the Morse complex of a cycle. What happens if I take that cycle and I attach a single leaf? If I attach two leaves, I destroy the homotopy type. What about a single leaf? Well, we can prove that this will actually strongly collapse to the path disjoint union of leaf, which seems a little bit weird, but let me show you why this is true and then how I can use this to do some computations. So what I'm going to do is I'm going to look at the Hasse diagram of the cycle wedge a leaf. So the 4 vertices there, I guess the 8 vertices there on the left are the cycle. This is a cycle of length 4, and then I've wedged on a leaf there, this VW. And I want to play the same game with dominating arrows here. I can do the same game with the Hasse diagram. So I'm going to look at this blue arrow here, and I claim it will actually dominate both of the red arrows coming out of V. And so if you reflect on this, you take this definition into the world of Hasse diagrams, this will also work. And so I can pull off the 2 arrows coming out of V. And this argument works for any cycle wedged a leaf. Well, now what I'm looking at is the Hasse diagram of a path of, on 1 fewer vertices, disjoint union a leaf. This VW on the right is a leaf, the Hasse diagram of a leaf. And the thing on the left is actually the Hasse diagram of a path, but it's kind of upside down, right? It's upside down, but that doesn't really matter. I only care about the relations that it has. And so this collapses the homotopic, or the Morse complex of a cycle wedge or leaf, strongly collapses to this Morse complex here. So what? Well, another result we were able to show, which took a little bit of work, but this is turned out very nicely, is that the Morse complex behaves very well with respect to disjoint unions. So on the left there, I have the Morse complex of a disjoint union. On the right, I've got the join of 2 simplicial complexes. And we know fairly decently how joins behave. We know how the connectivity works. If I know the connectivity of both products, or both factors, I know the connectivity of the product. I know if one's collapsible, then the join is collapsible. If I have spheres, I know how these things work with respect to spheres. There's these nice ways that I can take these joins of spheres. And so this result holds here. And so now what we can do is combine these 2 results and put them together with Kozlov's result to prove that the Morse complex of a cycle wedge a leaf is given by this. So the Morse complex of a leaf, well, it's just a single path on got one path, and so I've got 2 arrows, they're disjoint, so I've got an S0. So essentially this gives me like a suspension, since I'm joining it with S0. It's giving me a suspension on these things. Okay, so this is the Morse complex of a cycle wedge a leaf. Let me show you one more before I move into something a little bit different, which is, this is a centipede graph, I believe. Right? I always confuse it if it's centipede or caterpillar, but I think it's a centipede graph. Centipede graph, I don't know. Anybody knows these things? Okay, centipede graph. So there's a graph, is a path with a bunch of little legs there. We can pull the same trick using some of the results we've seen before to compute the homotopic type of this Morse complex. And that's going to be by just finding some dominating arrows. This blue arrow dominates this red arrow. Again, think about every single gradient vector field that contains the red arrow. This blue arrow is compatible with it. And so I can pull this off. Well, now I can just kind of move on down the line and keep pulling things off. Now this blue arrow will dominate this red arrow. And so not only can I pull off this red arrow, both of the arrows that were on that edge are now gone. So with pulling off the red arrow, I can pull off the edge as well. And now you can see inductively, I just keep on going right down the line, and I can just pull off all these edges there to get that the homotopy type of this centipede graph is the same as the homotopy type of a disjoint union of a bunch of leaves. I can apply our earlier result, and so I get just a bunch of joins of S0s. And so that's going to give me a sphere of dimension V-1 here. Okay, so that's a little, those are some homotopy computations. We'll see if I have time at the end to get to some other homotopy computations. No, probably not, actually. But the next thing I want to tell you about is something a little bit more relaxed, which is the connectivity. So it's often very difficult to compute the homotopy type of something. And so we have to settle for invariants, things that will at least distinguish things. And one nice homotopy invariant is the connectivity. So this is going to be, we're going to say a space is n connected. if all of its homotopic groups are 0 up to and including dimension n. And that doesn't mean it couldn't be 0 higher up, but this is a nice way to at least be able to tell some spaces apart. So what we want to do here is actually use something called Vespina-Brady-Morse theory, which is due to Matt Zaremski, although it originally goes back to Vespina and Brady, geometric group theorists, but Zaremski a few years ago was able to come up with a really nice paper that kind of unified several different Vespina-Brady-Morse theory with Foreman's discrete Morse theory. And this is a very nice theory. I highly recommend his paper. He was able to do some wonderful things like compute the Vietoris-Rips complex of spheres, not just simplicial approximations of spheres, but spheres up to radius 1/4. And so this works for things that are infinite. So it's a really powerful kind of thing. I think there's a lot of potential there. But I want to maybe just mention kind of in passing this Vespina-Brady-Morse lemma that Zaremski was able to prove, which essentially says that if I'm able to study something called descending links on a simplicial complex, these are going to be the links of a vertex up to that dimension, that level that it's in. I'm going to kind of look at the sub-level set when I'm first attaching that simplex, and then I want to look at its link. This is going to be called the descending link. And essentially what Zaremski shows is that if I have a nice study of these descending links, then I can get an isomorphism on these homotopic groups up to this certain dimension. So it's a kind of connectivity result. It's not going to give me the full-blown homotopy result unless I'm able to show it for all values, but this is going to give me some nice estimate here. So I'm going to come back to this and use this in a little bit. So before I show the result that Zaremski and I are able to show, we're going to also use a couple of results from Belk and Forrest, who defined the following. They said that a simplex in a simplicial complex will call R ground if every vertex of the complex is adjacent to all, but at most R vertices of the simplex. This definition is a little bit tricky to think through. I'm going to give an example in a second, but essentially I'm looking for a simplex that the entire complex is highly connected to. Most everything is connected to it, with all but some exceptions, and I'll show this in a second. And the point is, they were able to show that if you have a KR grounded flag complex, then I can get some estimate on the connectivity. So I'm going to kind of want to combine this Belk-Forrest result, this result of Zaremski about the connectivity of the Morse complex of my simplicial complex, in order to get an estimate on the connectivity of this Morse complex here. And in fact, one thing that might be a problem is that this is only for a flag complex, and in general, my Morse complex is not flag, but we'll get around that in a moment. So let me first just illustrate this idea of being a K ground. So let's go back to my generalized Morse complex. And it's not too bad to see that every K simplex of my generalized Morse complex is actually a K2 ground. So what this means is that if I have a K simplex, then it's connected to all vertices, any vertex is connected to all vertices of that simplex, except for at most 2. And so the way to illustrate this is the following. Let me take sigma to be that 2 simplex up there. I claim it's a 2-2 ground. And so the idea is that every vertex that is not in sigma is connected to every vertex of sigma with at most 2 exceptions. Okay, in this case, I can kind of see this pretty clearly, but let me illustrate why this is the case in general. So the orange vertex there on the right is represented by the arrow there on the left. And so what I'm looking to do is overlay the gradient vector field, or I should say the discrete vector field, given by sigma, which is the red. And so what I'm going to ask is, when I look at this red cycle here, how many of the arrows in the red cycle is this orange arrow compatible with? Or in other words, how many is it not compatible with? And I can see that it's not compatible with 2 of them. In fact, if I were to make this cycle of length 50, a really huge cycle with all these red arrows, there would only be 2 arrows, and I'll show them there in blue, for which this is not compatible with. So this is kind of the idea here. And so those two blue arrows are represented up there, and you can see them. So this is kind of the idea. So let's see. Okay, we're doing about 5 minutes. Show you a couple of the results that Zaremski and I were able to show here. First of all, if K has a vertex of degree D in the one skeleton, then I immediately get some sort of estimate on the connectivity of this Morse complex. And so what I like about this is there's absolutely no restrictions whatsoever on my simplicial complex. So what this lacks in accuracy in terms of homotopic type, it makes up for in generality. This will give me an estimate for any simplicial complex at all. If I want to be a little bit more specific and restrict to graphs, I'm able to get an even better estimate. So let's let G be a graph, and I'll let D of G be the maximum degree of a vertex in the Hasse diagram. Okay. Let's also let E of G be the number of edges of G. Then I get that the Morse complex is this thing connected. And if you think back to this Belk-Forrest result, this is precisely the form that Belk-Forrest gives us. So essentially, I'm going to want to apply this Belk-Forrest result. But one thing that's going to stop me is the fact that this is not a flag complex, so that Belk-Forrest does not apply directly. Well, this is where I'm going to use the generalized Morse complex as a kind of intermediary. And I'm going to just quick walk through a sketch of this proof, which is the following. First, I want to find a simplex that has the right grounding in my flag complex, in my generalized Morse complex. That's not too bad to show. Once I've got that in the generalized Morse complex, well, I can hit the generalized Morse complex with Belk-Forrest, and I can say that the generalized Morse complex has the connectivity I'm interested in. But I'd like to argue that not the generalized Morse complex, but the Morse complex has this connectivity. Well, the way I can do that is I can set up a Besvina-Brady discrete Morse function and then apply the Besvina-Brady lemma. And so the Besvina-Brady Morse function that I'm going to define is going to be, I'm going to take a vertex and I'm going to send it to the number of cycles that it is a part of. And so if you think about that, if it's 0, well, then I'm talking about the Morse complex. And if it's all of them, well, then I'm talking about the generalized Morse complex, and then I can have anything in between, the number of cycles that a particular vertex is involved with. What I want to do to apply this Morse lemma is now have an analysis of the descending links. And so you can show that the descending links break up into a join of a couple of other descending links. I forget what he calls these, maybe the lower and upper descending link or something like this. And now I can study the connectivity of these two guys. And so if I can prove that these two guys have the right connectivity, I know how connectivity behaves under joins. I'll show that they have the right connectivity, and then I can apply this Besvina-Brady Morse lemma, which says that the connectivity of this guy, this level subcomplex way up here, which is the generalized Morse complex, has the same connectivity as this guy way down here, which is my Morse complex. So we hit it with that, and we get this result, which I think is pretty nice. Okay, so if I'm thinking about time, that is, yes. And then so you can, there's some examples here. We can get, for example, an estimate on the connectivity of a complete bipartite graph, for example, or any other graphs you want. So this gives us at least some information about this stuff. Okay, so I'm just about out of time. I'm going to skip the last stuff here. We've got some, maybe let me just show you this result. This is a one general result that we have, which is not, again, not too bad to prove, is that I mentioned that part of our program is to try and compute the homotopic type of all trees. I at least have the form of all trees. We can show that the Morse complex of all trees is a suspension. And this is going to be using something of Barmak's called the star clusters. If you've seen that before, it's a really nice thing. And but I don't want to. I like to respect time. Okay, so stuff, things. Oh, these things have a lot of things come together. Oh my goodness. What was I thinking? Why did I think I could get through all this stuff? We also have the Morse complex of these things as well. That's a lot of fun. Blah stuff. Okay, so maybe the very last thing I want to do is just talk about some open questions where we still are. As I said, I was interested in computing the homotopic type of all trees, Morse complex. We've made a decent way there, but there's still a lot of ones to be done. If I want to go beyond trees, let's just go cycles. There's a lot to be done there. I was able to do a little bit by adding a leaf onto a cycle. That's not terribly exciting. So complete graphs, bipartite graphs, etc. And then in general, just Morse complexes, maybe of just the n simplex. This is really out of control. Justwick and Shari were able to show that the Morse complex of delta 3 has B1 equal 99. So this thing blows up really quickly. I've been thinking about ways to try and compute the Homotopic type of this, but so far it's been pretty unsuccessful. So there's it's completely wide open in higher dimensions. And then further relations between these matching complexes, the Morse complex, the generalized Morse complex. As I said, any result that I showed you about trees holds for the barycentric subdivision of the matching complex, and that's pretty easy. But are there any deeper relationships? And finally, applications. Is there any way that I could understand what I'm doing in a real life setting? I don't know, but I would love to be able to do so. So, dziękuję.
Thank you. Questions for Nick?
Thank you very much for this very nice talk. I have a question about the very beginning construction. You have the sequential complex, and you make that Morse complex out of all of the gradient vector fields that you can put on the simplex. It's kind of huge complex at the end.
Yes.
Can you, in the first step, consider, I don't know, some kind of critical simplices of these gradient vector fields and make a smaller Morse complex in the first step, which is kind of has the same homotopy type as what you are using here, and then go forward with what you have done?
Yeah, that's a good question, and I don't know if there's a way to do it, because in some sense the Morse complex is so sensitive to certain information. I don't know how I would use the critical simplices of the gradient vector field in order to simplify it somehow.
Mm-hmm.
If you have ideas, I'd love to talk more, but yeah, I don't have any ideas.
Thank you.
You're welcome.
Yeah, so thank you for your interesting talk. So I have a question, a little comment. So first, just a little comment. So it's a little bit confusing when you call this a Morse complex, because I think a Morse complex there is something else, and usually you would expect the homotopy type to be the same as the original complex, or at least the homology same as the original. I think in this case that's not true.
Yeah, that's right. I know you tend to think of it as the chain complex that's leading me to computing the homology using.
Right, I think in Foreman's work also there
Yeah.
was this Morse complex, which is something which computes homology of the original thing.
Yeah, point taken.
Yeah, no, but this other thing. So when you're looking just at the graph, so when your simplicial complex is dimension 1, then this Morse complex, if I understand correctly, it's the same as what we call complex of directed forests, correct? That's why this results was the same.
Yeah, that's right.
Yeah. So if that's the case, then I think you can save some of this questions which you want to work on, because so for the complete one, we also know what the answer is, and it's they're shellable and they're registered. I'm sorry I didn't react during the talk because it was 23 years ago with this paper. So I had to pull it up myself. But there is this paper, Complexes of Directed Trees, and I suggest you look at this. So some of this is in there. So the directed, if you have a complete graph, then we know the answer. And also, if you look at this other program that you want to compute it for all the trees, there is also the answer there. There is a recursive procedure which will compute the homology for all the trees. Not the homotopic type, so you may still think about homotopic type.
Okay.
But for the homology, there is a procedure which will do it for all of them.
Okay.
And there are many partial results which I believe will also fix the things you were thinking about when you attach edges. So I don't know, but for the trees, for the homology, we know the answer.
Okay. thank you. I appreciate
Yeah,
it.
so because you probably looked at the book, and it's not in the book, but you should look at this paper, Complexes of Directed Trees, and you just look section 4.
Okay, yeah, thank you. I appreciate that. Thanks.
Other questions? Well, let's go with seniority this time.
Just short question. What is the smallest example which is not wet of cells? The homotopic type is not wet of cells.
So as far as I know, I don't know the homotopic type of anything that isn't wedge of spheres.
And is it conjecture at least for forest, for trees, that it is wet of cells?
It's not conjecture. I don't think we have enough data to conjecture that. Yeah, I mean, this is one of those things where it seems like everything should be wedge of spheres, but that's kind of our only tool, or at least for me. We know how to recognize those. So
I add that a small connection to Hovanov homology when similar, but then we conjecture wedge of cells, maybe without enough data, but it will make talk for much.
thank you.
So I have one question about this homotopic type of this Morse. Is there some way to tell something about the homotopic type of the Vietoris strips filtration of your original space? Like in the case that you consider the cycles, the homotopic type resembles something that we already have the results for Vietoris strips filtration. So it somehow matches, but then let's say that at least you are constructing your graph by the one skeleton of Vietoris Rips filtration. And then you just construct this Morse simplicial complex. And then is it something to be able to say about the original space or not?
Something to say about the original space in terms of like is
The
Vietoris strips?
homotopy type of the Vietoris Rips filtration of the original space.
Yeah, that's a good question. I don't know.
Yep.
Yeah.
The construction seems similar on S1. I can send you the paper by Henry and his collaborators. They exactly took the same cyclic graphs, but then they have some other edges. But it might be possible that just beside taking the click complex of that construction, you can just use this Morse filtration and Morse function and simplicial complex to obtain the same result. And then it could be like generalized to more complicated situation.
Yeah, so I'd be happy to talk with you offline and be interested in hearing more about that. Thanks.
Yeah, so first, thanks for the great talk. When you consider this homotopy type of the Morse complex, and in particular, you also consider like homotopies between gradient fields, right? So
it depends what you mean by homotopies between gradient fields.
a pass in the Morse complex, I would say.
Okay, so like just the idea that I can homotop it down in the sense of maybe like doing strong collapses or something like this.
Yeah, for example.
Okay, yeah, okay.
Is there a, or well, I guess what I mean is that if you talk about the homotopy type, then yeah, you somehow talk about actual homotopies of functions from your space to itself, right?
Yes, that's right.
So,
Yeah, now I see
so
what you're
also kind
saying.
of like,
Yeah.
Yeah. And
Gotcha.
so with this notion, are there some kind of results like if I know that two gradient vector fields are homotopic in this sense, does there follow something from that? Is there any result of any kind?
I'm not sure about that either. Yeah. So I mean, I know what you mean by the Morse complexes and the homotopy between them, but I'm not sure like what gradient vector field or the homotopy between gradient vector fields.
I mean, the gradient vector fields are somehow simplices in your complex.
Yeah.
And so, yeah, okay, maybe it's a bit ill-defined because I would need to have a pass from like one simplex to another. So
yeah,
maybe one would need to find out what to mean by that. But
yeah. So I think I see what you're kind of trying to do here, and that's I don't think anything's known about that, at least not that I know of. How you might maybe quantify that.
Yeah, okay.
There's so many questions and so few answers. Anybody else is interested to ask a question? Anybody?
I've got a non-answer for you.
So you mentioned these ground simplices. What was the original motivation to introduce them?
Which simplices?
These ground simplices.
Oh, that's a good, that's, I'm gonna give the same answer. I'm not sure. So this was something that Matt knew about, you know, like just RK grounded simplices. Yeah, I'm not sure. So he came to me with this result and we applied it. I'm not sure what the motivation there was. Other than the fact that it kind of says, I mean, I think I can conjecture that in some sense it says that there's this strong attraction to, you know, a K-simplex in your simplicial complex, because you have so much, all the vertices have so much connection to them.
I was asking this question, I was pointing to Frank because, you know, all the complicated triangulations for, you know, crazy Morse functions that may have many additional critical cells that are kind of contains in the construction. And that's,
Yeah.
I think very intriguing. I think when you start to think about it for those complicated triangulations, you may see something interesting. It's not just in your head. Okay, maybe in the interest of non-Morse theoretical people, let's turn it offline. We can have the, you know, the curtains going on and we can have a pause so we can have a chat. Lunch is served from 1 o'clock, so you have this good for half an hour to talk to me. Let's thank you again. Very nice, thank you. Let me stop the streaming.